Hello, everyone. Today I'm going to talk about some discrete distributions. They are Bernoulli distribution, geometric, binomial, negative binomial distributions. Those last three distributions, they are really closely related to Bernoulli distribution. So I put them together.
Let's have a look at Bernoulli trial first. A Bernoulli trial is any random experiment that has two outcomes. Because there are only two outcomes, for the sake of convenience, we just name one of them success and the other failure, S and F. And usually there's no emotion is attached. For example, toss a coin once, it's a Bernoulli trial. You have heads or tails. Pick a ball at random from a group of black and white balls. Two outcomes, black or white. And you take a pass-fail exam, two outcomes, pass or fail. Now, Bernoulli trials as a probability concept is more than just a sequence of Bernoulli trials. Well, they're the same words, same phrase, but it's not a sequence of Bernoulli trials. We're going to talk about the difference a little bit later because obviously these phrases are exactly the same. But we do give several more meanings, some more meanings about Bernoulli trials rather than a group of Bernoulli trials. Okay, so we require three conditions. One, all trials need to be Bernoulli, that's obvious. Second, all trials are independent. And three, all trials have the same probability of getting success. And this probability is usually denoted by little p, so p equals the probability of success. Some examples that are Bernoulli trials. So we toss the same coin repeatedly. Or we select samples from a group of the balls, black white balls, with replacement. Some examples that are not Bernoulli trials. You toss two coins. These two coins are different. One is fair and the other is not fair. And you toss them alternately. Now, this each toss is a Bernoulli trial. So you put them together using plain English. That is a group of Bernoulli trials. However, we don't call them Bernoulli trials because they violate the third condition, which requires the probability of success to be the same. But here you have two different coins. The probability of successes are different. Another example that are not Bernoulli trials. Say we select samples without replacement. For example, you select two cards from a standard deck of 52 cards without replacement. Now, the probability that the second card is a heart would depend on whether the first card is heart or not. So this situation violates the second condition, which requires all the Bernoulli trials to be independent. So these examples show Bernoulli trials are not just a group of Bernoulli trials. All right, so let's look at the Bernoulli distribution. The Bernoulli distribution is to model any two outcome events. So the keyword of the keywords would be two outcome event or events. All right. So if we introduce a random variable x equal 1 if a success appears, and 0 if failure appears, then we have the following distribution. So you have 1, you have 0, and their probabilities. You would have p and 1 minus p. Sometimes we use a notation q to denote 1 minus p. So it's you can use it as a table. Or we can use a function f of k equals p to the k times 1 minus p to the 1 minus k. And k takes only two values, 0 and 1. Either way is fine. You have to use a table or the function. So that's the distribution. And its parameters, we usually use the mean and standard deviation. So our mean is just p, And the variance is PQ, so variance sigma squared is P times Q. We can calculate it very quickly. Maybe you'll spend some time doing that. So you have 1, you have 0, you have probability P, you have a Q. So mean equals 1 times P plus 0 times Q, so just P. And the second moment, E of x squared equals 1 squared times P plus 0 squared times P. You also get P. Then the variance would be equal to E of x squared minus E of x, which is mean, then squared. So you have a P minus P squared equals P times 1 minus P, or P times Q. Let's introduce geometric distribution. Usually a textbook would introduce binomial distribution first, which the reason is that binomial seems to be more important, more commonly used in reality. But I found that geometric distribution is easier to understand. So let's just work with this first. The meaning of a geometric distribution is to model the number of Bernoulli trials needed to see the first success. I would usually say the keywords are first success. Let's call this number of Bernoulli trials needed to be x, a random variable x. So what is the sample space of x, which is a group of numbers that x can take? Well, you have to have one trial. If the first trial is a success, you stop. And then x would be equal to 1. But maybe you don't see a success, then you have to continue try. So it's possible to have 2 trials or 3 or whatever. That's the sample space of the random variable. Let little k be any positive integer, 1, 2, 3, 4, and so forth. Then event x equivalent k means that the first k minus 1 trials are all failures, and the case trial is a success. Okay, that's implying that the first success appears in the case trial. All right, so the distribution, the probability, for the moment it's a probability, when x equivalent little k, can be found by using independence, because the first k minus 1 trials are failures. We have 1 minus p to the k minus 1, and the last one is a success, so multiply by p. Its parameters, the mean would be 1 over p. And the variance would be equal to 1 minus p over p squared. There's a reason why it's called a geometric distribution, because if you let k change from 1, 2, 3, 4, and so forth, you would have a sequence of what's a geometric sequence. We can use some facts about geometric sequence to find mu and variance, but I'm not going to do it here. All right, I just wanted to mention a little bit about the mean. It's the expected number of trials needed to see the success, the first success. So if the probability of success is really small, then you would need more. You would need more trials to see the first success. So you have this reciprocal relation. If p is bigger, then the expected number of trials needed would be smaller. Okay, so I want you to make sense out of this relation. It's not a proof, but at least it makes sense. The next distribution I want to introduce is a binomial distribution. The meaning of binomial distribution could be expressed by the following sentence. Right? It's to model the number of successes in n Bernoulli trials. The keywords, the number of successes. N is usually fixed. It's the total number of trials. It's different from geometric distribution, which doesn't have a fixed number of trials. What is the sample space of X? Well, it's possible that there are no success at all in n trials. So X should be 0. X is the number of successes. All right, it's a random variable. It could be 0, no successes, 1 success, and all successes, which is n. Let's try to get the distribution by the meaning of the random variable. For k equaling 0, 1, and so forth to n, the event x equaling k means that there are k successes in n Bernoulli trials. Okay, there are k successes in n Bernoulli trials. So how to find the probability of x equaling k? Let's look at a simple example. Toss a coin with probability of heads being 2/3. So it's not a fair coin, right? It's general. It doesn't really matter, little p is 2/3 or some other number. I just don't want you to treat any coin as a fair coin. All right, so probability of heads, 2/3. You should toss this coin 5 times. So Bernoulli trials, 5 Bernoulli trials. What is the probability of having 3 heads? This sentence implies that there are exactly 3 heads. You should not be confused by at least 3 heads or at most 3 heads, or this kind of phrases. That means exactly 3 heads, which also implies that there are 2 tails. Okay, this is important. There are 2 tails. Totally, you toss 5 times. You cannot forget about the other 2 results, the results of the other 2 tosses. Okay, they are all tails. Now, in order to find the probability that there are 3 heads in 5 tosses, let's take one outcome of these 5 tosses. This is HHHTT. Now, using independence, well, we're talking about Bernoulli trials, okay? Those trials are independent. So the probability of HHHTT would be simply the product of the probabilities. And the probability of H is 2/3. So we have 2/3 to the third times 1/3, which is the probability of getting tails, and 2 of them, 2 tails. But it's possible that outcome of 5 tosses is HTHTH. We say there are 3 heads. It doesn't mean the first 3 have to be heads, the other 2 are tails. These 3 heads could be anywhere in those 5 tosses. So this is another possibility. And the probability of this outcome, if you multiply all the probabilities, you will get the same thing. It's exactly that. So they have the same probability. And all the other outcomes that have 3 heads and 2 tails will have exactly the same probability, which is 2/3 to the third times 1/3 squared. So you add them up, and you only need to figure out how many such outcomes are there in 5 tosses. That's the counting problem. And we know that the number of outcomes that have 3 heads in 5 tosses is 5 to 3. That's a combination of 5 to 3. Okay, there's another video which talks about counting techniques, which I'm not going to talk about here. All right, so the binomial distribution is given by f of k. K is from 0, 1 to n. That equals n choose k. C is a combination, choose k, p to the k, and 1 minus p to the n minus k. All right, its parameters. Its parameters, we have mu to be n times p, and sigma squared, which is the variance, is n p q. Q is 1 minus p. The name binomial, the binomial distribution, the name binomial comes from the binomial theorem, which is a plus b to the n, expanding a plus b to the n, which equals the sum of n choose k, a to the k, b to the n minus k, and k runs from 0 to n. So you see this is very similar to this form. if you let P, A be P and B be 1 minus P, and expand it, you would get that. And also you would know this is indeed a PMF, it's positive, and add them up, you get a P plus 1 minus P to N, which is just 1. That shows this is a PMF. We can use some mathematical skills involving the binomial theorem to show mu is n times p and sigma squared is n pq. I wanted to introduce a different way of looking at it, but we need a little bit more property about expectation of the sum and variance of the sum. But it's very easy to understand, so I'm going to just go ahead and talk about it. X is the number of successes in n Bernoulli trials. So I'm going to introduce n random variables, x1 and then xn. Each one is a Bernoulli random variable. So all of them are Bernoulli random variables. If it's 1, you see if it's success, you have x1 to be 1. If it's a failure, now you have x1 to be 0. So the summation of these xn Bernoulli random variables is exactly the total number of successes in n Bernoulli trials. But expectation is linear, right? You can find expectation of the sum as the sum of the expectations. But all these expectations are the same. We calculated earlier, which is p. So you have n times p. Now the variance of x, because we have n Bernoulli trials, all these random variables are independent. Well, we didn't introduce the concept of independent random variables here, but there's another video that talks about that. There's a property of variance of the sum. If they are independent, if the random variables are independent, then the variance of the sum equals the sum of the variances. So you would just add these variances. All right, so what I said was that if xi's are independent, then the variance of the sum equals the sum of the variances. Okay, and we calculate the variance earlier to be pq, so that's npq. That shows the variance of the binomial distribution is npq. All right, that's about the binomial distribution. By the way, all the other properties, how to calculate the probability of certain events, all these examples will not be given here. Here, I'm just talking about the meaning of these distributions and how to get the distribution. All right, let's move on to the next one. Negative binomial distribution. It's actually a generalization of a geometric distribution. So the meaning of a negative binomial distribution is to model the number of Bernoulli trials needed to see the first R successes. So the keywords are the first R successes. When R equals 1, we get a geometric distribution. Okay, so the sample space, well, you have to see R successes. So you have to have at least R trials. So the sample space, the values that X can take, X the number of trials needed, right, to see the first R successes. So X can take values from R, R plus 1, and so forth. Let's look at the meaning of the event X equaling K. So let K be any integer greater than or equal to R. That could be R, greater than or equal to R. What does X equaling K mean? Well, you're going to see R successes, and it's the first time you see R successes. So the last one has to be a success. And the last one is actually the Rth success. So the case trial is a success, or X equaling K means case trial is a success. And there are R minus 1 successes in the previous k minus 1. K minus 1 trials. See, there's a typo here. K minus 1 trials. Now, the thing is that during the first k minus 1 trials, we know there are minus 1 successes, but we don't really care the order where they are. Maybe the first r minus 1 trials are successes or somewhere else. So this is exactly a binomial distribution. Okay, you can use a binomial distribution to model the second part. All right, so here comes the distribution. So for the second part, which is that there are r minus 1 successes in the previous k minus 1 trials, we have k minus 1 times r minus, choose r minus 1. It's binomial, right? P to the r minus 1 times q to the k minus 1 minus r minus 1. So minus 1 cancel it out. You have k minus r. But then you're going to incorporate part 1, which is this last trial is a success. You simply multiply by p. Okay, so this is the probability of x equal to k. So that is the distribution, PMF of negative binomial distribution. So let's rewrite the distribution. F of k equals k minus 1, choose r minus 1, to the p, originally you have r minus 1, but you multiply by p in the end, you have r, and then q to the k minus r. It looks like a binomial distribution, but no, they're not the same. If it's binomial, you have k choose r. Okay, you have k choose r. But here you have k minus 1 choose r minus 1. Oh, by the way, k would be from r plus 1, so forth. It has something to do with expanding a plus b to the negative negative power. So that's why you have a negative binomial, the name negative binomial. I'm not going to talk details about that. Let's look at the parameters, the mean. I'm going to use a similar way of getting the parameters of a binomial distribution to get the parameters of a negative binomial distribution. Because we have r successes. Okay, so let's look at all these k trials. So you have k trials. You have k trials. And the last one, here is k minus 1 trials. I have r minus 1 successes. And the last one, the case trial, is a success. Okay, now I can express x, which is negative binomial random variable. Okay, it's the number of trials needed to see r successes. I'm gonna express this x as the sum of r geometric random variables. Okay, so this is the number of trials needed to see the first success. Okay, so one is gone. And then the second one is the number of trials to see the first success after the first success. So actually the second success. But each one is geometric. Okay, each one is geometric. To add them up, that's exactly the number of trials needed to see the first r successes. But then we can use the property, the parameters of a geometric. So we know E of x, which is for negative binomial, is r times 1 over p. And the variance of x, which is our sigma square for negative binomial, equals r squared times 1 minus p over p. So hold on a second, that's so wrong. It's r times 1 minus p over p squared. Okay, that is about these several distributions I want to talk about. Some examples, details will not be mentioned here. This is to introduce their relationship and similarities. That's for today. Thank you very much. Bye-bye.